Well, hello there, warm welcome. Thank you for joining here. We're sharing the whole window. Grab a notebook, a pencil, or a pen, and now, as well, open up Desmos if you'd like. I would recommend doing this problem without Desmos and just using a regular graphing calculator, but at the same time, you need to know how to answer these questions on Desmos and how to use Desmos as a tool, so feel free to use it as a tool. Now, if you don't already know how, when you watch the video, um, you'll kind of see how I'm using it as a utility, not as a crutch. Okay, so this is math from the void. Math coming at you out of nowhere, and today we have a problem from the 1998 BC exam, which is why I wouldn't necessarily recommend. I wouldn't necessarily expect this level of difficulty question to come up when you do have a tool like Desmos, but we'll see. We'll see how things develop as they release more and more AP tests over the years with the use of Desmos, or with the intended use of Desmos. Okay, so yeah, if I hadn't made it clear already, give yourself about 12 minutes. See if you can solve this. If you're a Calculus AB student and you're still here through this intro, you weren't scared away by the BC letters in the title, feel free to stick around and answer this one, because you can totally answer all three of these parts. There might be some lack of clarity on what this says, so let's just read this through really quickly. It says R is the region in the first quadrant bounded by the graph of y equals 8 minus x to the 3 halves. I've written that out here for you. The y-axis and the x-axis and the y-axis. Find the area of the region R. Find the volume of the solid generated when R is revolved about the x-axis. And then we have part C with a vertical line x equals k, which divides the region R into two regions, such that when these two regions are revolved about the x-axis, they generate solids with equal volumes. Find the value of k. Very interesting take on some integration. We're definitely going to be using integrals. This is about areas and volumes. So, if you've already given yourself a shot, if not, you can still pause the video. Come on back, and here we'll get started. So here's how I would approach the problem. 8 minus x to the 3 halves. It looks a lot like 8 minus x squared. Like the equation literally looks like that. And this is a power function, right? A power function is x to a power, kind of like a polynomial centered at the origin. So if this power is bigger than 1, that means it's not linear. That means it's going to have a bend to it. So it's basically something like, it may not be this sharp. It may just be like that or something. But it makes roughly the same shape that a parabola or any other power function would make if it were flipped upside down. And the other boundaries are the x and y axes. So yeah, in the first quadrant, it did specify that. So there's our region R, just in case you didn't know. And part A wants us to find the area of the region R. So this is obviously going to come down to taking an integral. Up to where are we taking this integral? Well, it depends on where this spot is located. We want to go all the way from 0 to whatever this spot is. And we can find where it is because the function is equal to 0. The y value is equal to 0 at that point. And so we have 8 equals x cubed to the 1 half. So that's actually how I'm going to write it. I'm going to write it as the square root of x cubed, which means 64 equals x cubed, which means 4 equals x. You can solve that very easily. It's not really difficult. And now we're simply going to integrate. Very easy. Integral from 0 to 4 of this function. We technically could do an antiderivative by hand, and I'm going to get in this habit of putting these parentheses here now that we're using Desmos. That's how it wants you to input your integrand. Don't just put the 8 and then a dx all the way at the end with no parentheses. It's not going to understand that. Let's take a look at what this should be. In fact, I'm just going to plug it into Desmos and copy and paste it there. So let's see, we're going to do the integral from 0 to 4. Oops. From 0 to 4. parentheses 8 minus x to the 3 halves power. Notice how it still doesn't recognize. You see this like exclamation point over here. It still doesn't recognize this. Still doesn't recognize it. What's missing? Of course, the differential dx. 19.2. That's our answer. Let's take that and slap it right there. 19.2. Oops. I guess I should also put equals and box it. Okay. Very simple. We just found the area underneath this curve in the first quadrant in that little region. Yeah. So part B. Find the volume of the solid. So we're going to use integral as well. Generated when r is revolved around the x-axis. Now this is a key moment because revolving around the x-axis, which in this case is revolving around one of the boundaries, is going to produce disks, solid kind of looking disks. Let's sketch it again. It's something like this, roughly. Make it three-dimensional and try to stick the z-axis sort of back there, sort of going back into the page, you know what I mean? Into the whiteboard. That looks kind of bad, actually. That looks better. Now what we're going to do is we're going to rotate this region around the x-axis so that we get these sort of slices. And the slices are circles, of course, because we're rotating this around the x-axis. These slices are changing in radius depending on how tall the function literally is. So the height of the function is the radius of these slices. So r equals the function, 8 minus x to the 3 halves. And so the area of each of these slices is simply going to follow the area of a circle. That's pi r squared. And in this case, we can put pi times 8 minus x to the 3 halves squared. Okay, great. Now, since we're using a calculator, we don't really have to work out what that is. We probably wouldn't want to work out what that is like this anyway, so it would just be some kind of a u substitution. Yeah, because we would have v equals the integral from 0 to 4, and we can stick the pi multiple out in front of 8 minus x to the 3 halves squared. That could be done with some u sub and all that good stuff, but yeah, we don't have to really worry about that. So actually, I'm going to leave this out. Let's see how it's plugged in on Desmos. I don't have to write these things anymore, so it's going to go much faster, honestly. These videos might end up going much faster. So this is going to be squared. Oops. Do I have a squared on the right thing? Let's see. Yeah, I do have a squared on the right thing. Squared, and this is also going to be multiplied by pi. I could have put it inside or outside, doesn't really matter. And what we're going to do here is take a little picture. And we're going to put these little picture right here. There we go. So there is our volume. We took the integral, make sure the expression's the same. Yep, expression's the same. Limits are the same because it's the same region. And we're good to go. That's part B. Super simple. All right, now part C is a little bit different. Because a lot of times they would ask a question similar to this, but they would ask for where the vertical line is k that splits the area into two parts. So it would be, I don't know, somewhere around here. You have to find out where that spot is. But this time we're trying to find a spot where it's going to make the volumes equal. And interestingly enough, it's not the same location that would make the areas equal. I know that doesn't seem to make any sense, but it's because these slices here are growing at a different rate than the slices here. So it's one thing for the space two-dimensionally to be the same, but if we're constructing solids from this, it's not necessarily going to produce the same volume when you rotate it around the line, right? Because it all depends on how big are those slices going to be. Are you going to rotate it around this line? Well, then the taller function is going to deviate like a lot because those are going to be bigger sections, bigger chunks. So not sure if that kind of made sense to you, but what we want to do basically is we want to find a spot so that these volumes, which they look like slices, they don't necessarily look like three-dimensional, but like up to a certain point, those slices will be like half of the total volume. And then the remaining slices, you can just sort of think about it as like a food, really, if it's like a loaf of bread. If you want the volume to be the same for two slices, if the bread's kind of misshapen like this at the end, then you're not just going to cut like halfway into it, right? And that's because the volume changes at a different rate than simply the height changes. Okay, so how would we even set that up? Well, what we would say is that in any event, these slices have the same cross-sectional area. They have a radius still of 8 minus x to the 3 halves. They still have an area of pi times that squared. 8 minus x to the 3 halves squared. That is still the cross-sectional area. So what we want here is we want the volume from 0 to k. In other words, we want the integral from 0 to k of this expression, pi 8 minus x to the 3 halves squared dx. We want that to be equal to the rest of the volume from k to 4 of the same expression, 8 minus x to the 3 halves squared. So if these are equal, of course, we can cancel the pi's right away. But here's exactly what I was talking about. We're going to have to take an antiderivative, or an integral, and we're just going to do a quick little u sub, because if u equals 8 minus x to the 3 halves, then du is equal to negative 3 halves x to the 1 halves. Which I guess we don't have there. Interesting. Okay, it looks like we'll actually have to just expand this. Never mind. False alarm here. I think we're just going to have to work all this out. So this is going to be 64 minus 16x to the 3 halves. Those can all be done with like a power rule. And then we're going to have plus x to the 3, I guess. Yeah, x cubed. And this is going to be evaluated from, all of this is going to be evaluated from 0 to k. And that's going to be equal to the same antiderivative. Oh, what am I doing here, guys? I have not taken an antiderivative yet. Oh, that's why it's putting in parentheses, because I need the dx still. Plus minus integral from k to 4 of all this is equal to 0, basically. Because if they're equal, then, their difference is 0. Okay, now it's time to take an antiderivative. So this is going to be 64x minus x to the 5 halves. But then we're going to divide by 5 halves. So multiply by 2 and then over 5. And then we have 1/4 x to the 4th. Of course, this is from 0 to k now. When you plug in 0, nice things happen. And then we have the exact same. Minus 32 over 5, x to the 5 halves, plus 1/4 x to the 4th. Now all of this, I'll put that in brackets, is going to be from k to 4. And this has to equal 0. So we're going to get some equation that's just in terms of k, and then we can probably graph it on Desmos in some way. In fact, I think some terms are likely to cancel, but not guaranteed. Let's just be careful about this. So we're going to have 64k minus 32 over 5k to the 5 halves plus 1/4 k to the 4th. Plug in 0, nothing happens. It's just everything's 0. Minus 64k minus 32 over 5k to the 5 halves again, plus 1/4 k to the 4th. Let's move all that, shall we? That's what you get when you plug in k. What about when you plug in 4? So this is going to get pretty hefty, I guess. You could probably use Desmos for a situation like this, but you don't really need it. 4 to the 5 halves is just 32. So this is 1,024 over 5. Or 204.8. Plus 1/4 of 4 to the 4th, so that's 64. All right, so we got some fairly decent sized numbers, I guess. Let's see, we subtract these two. And you can use Desmos for all this if you want to. I just kind of refuse to do that. 25, yeah, so 51.2 and 64. 115.2 minus, we have all these k terms, so let's distribute that negative, and then we'll distribute the other negative. 32 over 5, k 5 halves, minus 1/4 k to the 4th. And then when we distribute the negative on that, we're going to get minus 115.2. Here's our plus 64k. That's going to go along with this plus 64k. Then we have minus 32 over 5k to the 5 halves. That's going to go along with this minus 32 over 5k to the 5 halves. And then we have, this is going to be plus 1/4 k to the 4th. That is going to go together with our plus 1/4 k to the 4th. Okay, so we get a decent expression. You know, we have 1/2 k to the 4th. We have, what's the next highest power? We have minus 64 over 5 k to the 5 halves. We have 128k, and we have minus 115.2. That all has to equal to 0. So whatever k needs to be for that to be the case, that will be our value. So how do we solve that? We just use x on Desmos, and then we plug in this equation, and we see when it hits 0. So 1/2 x to the 4th minus 64 over 5 x to the 5 halves. There we go. Plus 128k, x, minus 115.2. It's very close to x equals 1, apparently. 0.9949. So that is our k value. You could say 995, I'm sure. And so that's the spot. You can see that it's pretty, again, if you have like a chunk of meat or a slice of bread, and you want to cut it with, give both kids an equal piece or whatever, you and your spouse an equal piece, whatever it is, you're not going to cut it halfway through, like at the x equals 2 mark. Right, you're going to cut it like right here, because we're not saying that this area is the same as this area. Instead, we're saying that if this is 3-dimensional, that the volume of that piece is about the same as the volume of this other piece, which I guess I'll... Right, it's like the big piece of chicken and the end of the big piece of chicken. Or like a potato. You don't necessarily have to cut it right in half for it to be like half volume. It could be misshapen. Okay, so that's kind of how we use Desmos. That's sort of how I'm going to be using Desmos, and I encourage you to start using it so that you can be prepared for that on your AP exam. But other than that, it is enough blab out of me. I think parts A and B were very, very straightforward. Part C was a little bit trickier, but you can notice that we didn't really rely on Desmos that much, except for like maybe one part of each problem, and that's it. You would get points for everything else that you did to set it up. Or if you didn't have a certain value, you would be able to just put like variables. If you didn't know it was from 0 to 4, for example, you could just if it wasn't clear, if it ended up being like the fifth root of 3.7, you could just leave it as that the whole time, and then at the end you might get stuck, but you would get points for every step that you do that is foundational establishment. Any kind of conditions or calc knowledge that might get you partial credit. Anyways, I said that was enough blab, so that's enough blab. I'll see you guys next time in the void.